Okay, so understand what was being shown by the picture, in inverted commas, drawn by the oscilloscope, we need to go back a little way. And this is the circuit diagram of what you're actually looking at. Here's the transformer, of course, and here's the primary winding, and it's being supplied with an alternating current. That's the symbol for alternating current. 240 volts going in, and I think there was about 4 volts or just under coming out. Now, of course, you and I know that the secondary winding would have far fewer turns than the primary winding, but this is only a schematic diagram. So here is the secondary winding then, and the top half of the winding comes out. Here's the diode, which rectifies the AC into DC, and here's the light bulb, and here's the return path back to the secondary winding. Okay, so what did we see on the oscilloscope? Well, the first part of the circuit where we placed the probe, the thing that detects the electricity and then displays it on the oscilloscope, was about here. We placed the probe about there. Tell you what, you can't see that very well. I'll draw an arrow in instead. There. So this was the alternating part of the circuit, the alternating current part. AC goes into a transformer, AC comes out. And we placed the probe here before the diode. And what did we see? Well, let's have a look. Just change pens. On the oscilloscope screen there was a centre line, if I can draw a straight line, which denoted 0 volts. 0 volts. And keeping the camera still as best I can, a line emerged up in a kind of arc, rather like a ballistic trajectory actually, we won't go into that right now, and did that. Now, what you might have seen on the oscilloscope screen was, in fact, there's a grid on the screen, rather like the graph paper. And although it can be changed, there were various positions denoting different voltages. So at a position, let's say here, it denoted 1 positive volt. 1 volt plus, or positive volt. Then an equal way up there would have been another little symbol, and that would denote 2 volts of positive voltage. And then further up again there would have been 3 volts plus 3 volts. And again plus 4 volts, and so on and so forth. So what this told us was that as the trace on the oscilloscope rose, when the trace got to about this point here, the voltage was 1 volt. And when the trace got to about this position here, it was 2 volts. When it got to here, it was 3 volts. When it got to here, it was about 4 volts. But then the voltage started to drop off and came back down to 3, back down to 2, back down to 1, and eventually back down to 0 volts. The significance is that any part of the trace that is above the centre line, the centre 0 volt line, means the electricity was all going in the same direction. We'll say it was going in that direction. But of course the trace didn't stop here. It then went down below the line. I'm hopeless at drawing, so you'll have to forgive me. And any part of the trace that was below the 0 volt line meant that the electricity was travelling in the opposite direction. And down here there was a situation where we had a mark, and that would have meant minus 1 volt. And another one that would have meant minus 2 volts. And minus 3 volts, etc. etc. Now, when it says minus, it isn't like your bank account, which means that you owe the bank money. It simply means that the electricity is flowing in a different direction. And there's nothing wrong in that. So just to carry on, as the trace line, the picture that the oscilloscope drew, got to around this point, it meant it was 1 volt of electricity flowing in that direction, and then 2 volts of electricity flowing in that direction, and 3 volts in that direction, 4 volts in that direction, and then it started coming up. The voltage went from -4 to -3, and then -2, and then -1, and then back to 0. Of course, as we saw, it then continued on and did the same thing pretty much again ad infinitum. Now, points to note here, though you don't need to know it really at the moment, but it's come in handy later, that the distance that these peaks, positive peaks and negative peaks, form is known as the, if I can keep the slates clean, it's the amplitude. The degree that these waveforms go up and down is known as the amplitude of the waveform. You'll come up against that word amplitude again when you're dealing with another strange word called modulation. Amplitude modulation, AM, as you would see on a lot of broadcast receivers. And from here, this point here, to this point here, that is one complete cycle. One cycle. And the mains electricity that feeds our houses has a cycle of 50 cycles per second. Has a frequency of 50 cycles per second. This transition from a peak of positive voltage back to 0 and a peak of negative voltage back to 0 occurs 50 times every second. Okay. Then we put the scope, or the probe from the oscilloscope, into a slightly different position. Let's go back to that. We put the probe in a different position. We put the probe over here. And then the image changed quite dramatically. It changed to that, where the current is only flowing in one direction. Right. The current is flowing in one direction, but it's not flowing all of the time, because during the time when the current would have been flowing in the opposite direction, that was cut out by the diode. The diode only allows current to flow in one direction. So we have these seemingly almost random or rhythmic peaks of positive electricity. It's rather as if someone had a battery and they were turning the battery on and off and on and on and on and off and on and off and on and off very, very quickly. But what this means is that although we have direct current, we only have electricity travelling in one direction, it's not there all the time. From this period here to this period here, there's no electricity flowing at all. And that's why the multimeter showed such a low voltage, because multimeters work on averages of how much voltage there is in a circuit every second. They normally take about 3 sample voltages per second and work out the average, and that's why the voltage seemed to be so low. This is called, I think I mentioned just now, pulse electricity. But then we did something really rather, or not rather different, we did something very different. We put a capacitor in parallel with the bulb and the power supply. I'm going to draw this in dotted lines here. We put in a capacitor, and then the image changed dramatically again, didn't it? To understand what was happening there with the capacitor in place, we need to have a quick refresher of the characteristics of capacitors in a DC circuit. Let's do that now.